Assalamu alaikum. Bismillahirrahmanirrahim. Assalamu alaikum. Welcome to chemistry class, chapter 6, solids. Today, topic under discussion is allotropy. We will study its history, its examples, then allotropes of carbon, allotropes of oxygen, allotropes of sulfur, and the last will be transition temperature. Now, let us explain its allotropy. It is an ancient Greek word derived from two words allos meaning other and tropos meaning manner or form. It is the property of some chemical elements to exist in more than two or more than two different forms in the same physical state is known as allotropes of the element. Simply, it is when an element exists in different crystalline forms, these forms are called allotropes, and this phenomenon is allotropy. This concept was first proposed in 1841 by Swedish scientist Baron Johannes Jacob Berzelius. What is allotropy? Allotropy is the existence of elements in two or more forms, which may differ in the arrangement of atoms in crystalline solids. When a compound exists in different crystalline forms, then it is polymorphism. When an element exists in different crystalline forms, it is allotropy. Simply, we can say allotropes are different forms of an element, and polymorphs are different forms of a compound. Different bonding arrangement between atoms resulting different structures with different chemical and physical properties. When arrangement is different, when bonding arrangement between atoms is different, that results in different chemical and physical properties. Examples of allotropy. Few elements exhibit allotropic phenomenon. These are carbon, sulfur, oxygen, phosphorus, tin, silicon, and boron. Let us study carbon, sulfur, and oxygen allotropic forms. First are the allotropes of carbon. Carbon is capable of forming number of allotropes due to its valency. Allotropes of carbon are diamond, graphene, Q-carbon, graphite, linear alkylic carbon, fluorines, and carbon nanotubes. We will study diamond and graphite. Diamond is extremely hard, transparent crystal with carbon atoms arranged in tetrahedral layers. It is poor electrical conductor but it is excellent thermal conductor. While graphite is soft, black, flaky solid, and it is a moderate electrical conductor. Carbon atoms are arranged in hexagonal lattice and then in layered as sheets. इसमें दोनों अरेंजमेंट्स हैं, हेक्सागोनल लेटेस भी है और लेयर्ड अरेंजमेंट भी है. Allotropes of carbon with their peaks are, this is diamond, graphite, graphene, fluorines, and carbon nanotubes. Allotropes of carbon. We will study two most important forms of allotropic forms of carbon, that is diamond and graphite. Diamond exists in cubic form and here is its structure. It is hardest form, while graphite exists in hexagonal form and have a layered structure. Distance between two layers is 35.4 picometer. Let us compare the properties of diamond and graphite. Diamond is naturally occurring in free state. Graphite is naturally occurring as well as it can be prepared artificially. Diamond is hardest natural substance known, while graphite is soft and easy to touch. Diamond has high diffractive density of 3.5. while graphite has relative density of 2.3. Diamond has transparent and high refractive index of 2.45, while graphite is black in color and opaque. Diamond is non-conductor of heat and electricity, while graphite is good conductor of heat and electricity. Diamond, it burns in air at 900 degrees centigrade to give carbon dioxide, while graphite burns in air at 700 to 800 degrees centigrade to give carbon dioxide. Diamond occurs as octahedral crystal, while graphite occurs as hexagonal crystals. Diamond is insoluble in all solvents, while graphite is insoluble in ordinary solvents. Next are allotropes of oxygen. Oxygen has four known allotropes: dioxygen O2, which is common oxygen in gaseous state and it is colorless. Ozone is O3 and it is light blue in color. Tetraoxygen is O4, which is red in color. Metallic oxygen, it is obtained at very high pressure. We will study oxygen and ozone. Allotropes of oxygen. Most common forms of allotropes of oxygen are O2 and O3. Dioxygen or common oxygen, molecular oxygen O2 and trioxygen, that is O3, ozone, are the most common forms of allotropes of oxygen. These are obtained by absorption of heat from the atmosphere, that is 142 kilojoule per mole of energy has been absorbed, and it results in conversion of oxygen molecule to ozone molecule and vice versa. This is diagram for oxygen molecule that show two atoms combined to form oxygen molecule. Here is the ozone molecule in which three oxygen atoms are combined to give ozone molecule. This is the structure of ozone molecule in which three oxygen atoms are bonded together. Distance between two oxygen atoms is 1.278 angstrom and the bond angle is 116.8. Oxygen molecule has one sigma and one pi bond. In ozone molecule, bond angle is 116.8 degree. Ozone has characteristic smell and its concentration above 1000 ppm is very dangerous and it causes severe health hazards. Next is formation of allotropes of oxygen. Oxygen and ozone, these are present in our atmosphere and they both are interconverting into one another. UV radiations are important to bring these photochemical reactions. These conversions are spontaneous and one directional, therefore they are called monotropic. Maximum concentration of ozone is 10 ppm parts per million, and it occurs at 24 to 30 kilometers from surface of Earth, that is in stratosphere. Now have a look how it is produced in atmosphere. Ultraviolet radiations from the sun strike these diatomic molecules and split these diatomic oxygen molecule into oxygen atom, and this bond is broken with the help of UV radiations. Next, this oxygen atom is going to react with another dioxygen atom molecule and they will produce ozone molecule. Ozone layer in atmosphere. You can see this is sun, it is our earth, and these reactions are taking place in between. First, oxygen molecules are photolyzed. Photolyzed means break down in presence of sunlight. And These oxygen molecules break down to give two oxygen atoms, and this is very slow reaction. Second reaction is one ozone and one oxygen atom are continuously being interconverted. As solar UV breaks ozone and oxygen reacts to form another oxygen molecule fast. Here, this ozone and one oxygen atoms react in presence of UV rays and produced oxygen molecule. This interconversion process converts UV radiations into thermal radiations, heating the stratosphere. One more change occurs during this reaction is they convert UV radiations into thermal energy that results in raising the temperature of stratosphere. This is our second step. Now in the third step, ozone is lost by the reaction of the oxygen atom or the ozone molecule with each other or some other trace gas such as chlorine. This ozone is lost by another way with the help of chlorine or by using another oxygen atom. Comparison of oxygen and ozone. Composition: oxygen is diatomic while ozone is triatomic. Oxygen concentration is 21% while in stratosphere ozone is 10 ppm in concentration. Oxygen has no smell while ozone has pungent smell. Oxygen has one sigma and one pi bond in its structure and has linear structure, while ozone has angular structure with 117-degree angle. Function: oxygen helps in photosynthesis as well as in respiration, while ozone absorbs harmful UV radiations. It exists naturally in atmosphere while ozone is produced by photochemical reactions. Stability: oxygen is very stable while ozone can be easily decomposed to oxygen molecule. They both are in gaseous state. Oxygen is used medically to overcome breathing problems, in steel making to oxidize carbon from pig iron and oxyacetylene torches, while ozone is used in sterilizal in food shops and kitchens, in purification of water and as bleaching agent in paper and textile industry. Allotropes of sulfur. Allotropes has two classes in which its allotropes have been divided. Crystalline, these are rhombic and monoclinic, and amorphous, which are plastic, colloidal, and milk of sulfur. Colloidal uh, sulfur is also known as amorphous sulfur, commonly known as amorphous sulfur. Rhombic sulfur is also known as octahedral or alpha sulfur, or monoclinic is also given the name of prismatic or beta sulfur. We will study rhombic sulfur, monoclinic sulfur, plastic sulfur, and amorphous sulfur. Rhombic sulfur. Rhombic sulfur is crystalline in nature, bright yellow in color, made up of S8 molecules, and it is stable below 96 degrees centigrade. As you can see, it has very bright yellow in color. And here it shows you the structure of rhombic sulfur. It composed of 8 sulfur molecules. The next is monoclinic sulfur, which is also known as beta sulfur. It is also crystalline in nature. It can be converted to rhombic sulfur at room temperature. It is stable between 96 and 119 degrees centigrade. You can see its Color is lemon yellow, not bright yellow, and it has a very beautiful crystalline structure. Here, monoclinic sulfur can be converted to rhomboklinic sulfur and vice versa. Plastic sulfur. It is supercooled liquid. If yellow sulfur is heated to boiling and poured into liquid, it will roll up and produce plastic-like ribbons. It is not considered as true allotrope of sulfur because it is soft and elastic in nature and insoluble in H2S hydrogen sulfide. Next is amorphous sulfur. Amorphous sulfur has irregular crystalline shape and is known as amorphous sulfur. It is not found in sea state, but it can be prepared when H2S gas is passed through water for a long time. A saturated solution of H2S so obtained is exposed to air. Amorphous sulfur so produced has almost white color, very light yellow or nearly to a white color. Here is a chemical equation in which H2S gas is passed and oxygen is reacted and it gives you water plus sulfur. This sulfur is amorphous sulfur. Comparison of allotropic forms of sulfur. Form. Rhombic and monoclinic sulfurs are crystalline form, while amorphous sulfur and plastic sulfur are amorphous form. Plastic is amorphous and supercooled form. Color. Rhombic sulfur has bright yellow crystals. Monoclinic sulfur has lemon yellow. Amorphous sulfur has yellowish white, while plastic sulfur has yellowish brown soft ribbon-like structure. Stability. Rhombic sulfur is stable below 96 degrees centigrade. Monoclinic sulfur is stable between 96 and 119 degree. Amorphous sulfur is less stable than rhombic, and plastic is also less stable than rhombic sulfur. Solubility. Rhombic, monoclinic, and amorphous sulfur are soluble in carbon disulfide, while plastic sulfur is insoluble. Next is transition temperature. Transition temperature is the temperature one in at which more than one form of different substance can coexist in equilibrium state. This is the transition temperature. Above or below this temperature, only one polymorph or allotrope may exist. Like tin has two forms, gray and white, and these are orthorhombic and tetragonal crystalline forms. These both crystalline forms coexist at equilibrium at 18 degrees centigrade. Below or above 18 degrees centigrade, only one crystalline form may exist. Sulfur has two crystalline forms, monoclinic and orthorhombic. They both coexist at 95.6 degrees centigrade, and this is its transition temperature. I hope you have enjoyed today's lecture. Here is an assignment for you people. Define allotropy and name allotropes of carbon. Oxygen and ozone can be interconverted. How? Explain with the help of diagram production and destruction of ozone. Differentiate between rhombic sulfur and amorphous sulfur. Define transition temperature. Give transition temperature of potassium nitrate. I hope you have enjoyed the lecture. Thank you and have a nice day.